So far we've talked about sample spaces, how to count how many elements are in a sample space, and what events are. We've talked some vocabulary, but we haven't actually talked about probability yet. So today we're going to talk about probability. So we're going to get into probability of events, and we're going to find some basic rules that'll help us calculate some basic probabilities before we get a little bit more intense later on. So the definition of probability that's presented in your book says the probability of an event A is the sum of the weights of all sample points in A. Therefore, 0 is less than or equal to the probability of A is less than or equal to 1. The probability of the empty set is 0, and the probability of the full set S is 1. Furthermore, if A1, A2, A3, and so on is a sequence of mutually exclusive events, then the probability of A1 union A2 union A3 and union with all the rest equals the probability of A1 plus the probability of A2 plus the probability of A3. So this is a huge definition. So I'm going to break it into 3 parts, and we're going to talk about each of the parts along the way. So we've seen most of the words in part 1 before. So we're defining probability. We've seen the word events. We know that A is like what we use as a variable for events a lot of times. And we've seen the idea of a sum so many times in life. We've seen the idea of sample points in our event. But this idea of a weight, that's new for us. So when we talk about the weight of a sample point in A, because that's what we're talking about here, we're talking about the likelihood of that sample point being the outcome of a statistical experiment. The word weight and probability are used kind of interchangeably when we talk about a single sample point. So keep that in mind. An event is a collection of sample points, and so we're looking at the sum of the probabilities for each of the sample points, which will give us the probability of the event. In part 2, the potentially new part that we're seeing is this 0 is less than or equal to the probability is less than or equal to 1. So when we talk about the likelihood of sample points, each one of those points is one potential outcome of a statistical experiment. So say I have a statistical experiment of rolling a dice. I have 6 possible outcomes, and each number has a weight of 1 out of 6. It's 1 out of 6 possible outcomes. So if I look at all the possible sample points in my experiment, each one of them has a weight of 1/6. And since the probability of an event is the sum of them, then I'm adding up 1/6 6 times. And when you do that, you end up getting 6/6, which equals 1. And this is going to happen for any statistical experiment. So that's how we get our upper limit of 1 here, and why the probability of the entire sample space is 1. Now on the flip side of that, each one of these weights is a positive number. Each one of them is a fraction, like 1/6, 1/2, 1/512th, whatever. It'll be a positive fraction. So whenever I take the probability of a sample point, it's going to be something that's greater than 0. We're never going to get negative numbers in there. However, if we have something that just can't possibly happen, then we end up with a probability of 0, and that's how we indicate it. So that's where this idea that the probability of the empty set is 0, and I get my lower bound for my probability of my event. Now, everything in part 3 of this definition, 1 definition, 2 definition, 3 definition, 4 definition, 5 definition, 6 definition, 7 definition, 8 definition, 9 definition, 10 definition, 11 definition, 12 definition, 13 definition, 14 definition, 15 definition, 16 definition, 17 definition, 18 definition, 19 definition, 20 definition, 21 definition, 22 definition, 23 definition, 24 definition, 25 definition, 26 definition, 27 definition, 28 definition, 29 definition, 30 definition, 31 definition, 32 definition, 33 definition, 34 definition, 35 definition, 36 definition, 37 definition, 38 definition, 39 definition, 40 definition, 41 definition, 42 definition, 43 definition, 44 definition, 45 definition, 46 definition, 47 definition, 48 definition, 49 definition, 50 definition, 51 definition, 52 definition, 53 definition, 54 definition, 55 of us being able to take the sum this way. So just a reminder, when we saw mutually exclusive events, what this meant was that they didn't have any outcomes in common. So there's no chance that two of them are happening at the same time. So when we think about this sum, we want to be thinking about maybe maybe event A sub 1 is the probability of rolling a 1 or a 2. So each one of those have 1/6, so the probability of A1 is actually 1/3. Maybe sample or event A2 is the probability of rolling a 3, 4, or 5. So the probability of A2 is actually 1/2. And maybe A3 is the probability of rolling a 6, leaving it with a probability of 1/6. So each one of these events, since they can't overlap at all, it's basically like we're taking all of our events that we had before and we're adding them up. So we'll be adding up 1/3, 1/2, and 1/6 in this case, which is really the same as adding 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 all together. All right, so that's what's happening here. Because they can't overlap, we really could make one giant event out of them, which is what's happening when we take the union. We're putting them all together into one set. And what we're really doing is we're adding all of the pieces of probabilities together. We'll be looking more at this as we move on. So hopefully, as we were talking about adding up 1/6 6 times and thinking about our probabilities of, say, A2 was 1/2, it seemed a little bit absurd. And the truth of the matter is, most of the time you won't have to do something like that. Every once in a while you will, though. But most of the time, we have a rule that helps us out. So the probability of an event A equals a lowercase n over a capital N. And what these letters mean, so this is all set up with an experiment has n equally likely outcomes and A consists exactly n of them. All right, so all I have to do is throw a word when in there and in, and now I have a rule to follow that the probability of my event A equals lowercase n over capital N when an experiment has capital N equally likely outcomes, and my event A consists of exactly n of them. Now, everything we've talked about so far works great if we have equally likely outcomes in our sample space of our statistical experiment. However, that's not always the case in real life. So what we end up using is relative frequency. And this is the idea that if you conduct the experiment enough times and you observe every time what the outcome is, then you can assign likelihoods, probabilities, to each of the elements in your sample space. So if you have an unfair coin, for example, and you flip it enough times, you flip it a ton of times, and you observe the probability that it lands on either side. A fair coin would eventually, with lots of experiments, turn out to be a 1/2 likelihood for both sides. An unfair coin, however, could end up with any probability for the pair of sides. Now, if you have reason to believe that all of the outcomes are equally likely, what we tend to use is an indifference approach to probability. And what that means is I say, I think that the die is fair, and so I'm going to say the probability of rolling a 4 is 1/6. Now, gambling especially depends on people not taking an indifference approach. Instead, it depends on them taking a subjective approach. So with the subjective approach, you're using your personal beliefs, potentially that you've have an uncle whose lucky number is 3, and so that's going to be the way things go. You even might be using your intuition about something. That's all a subjective approach to probability. So when we're talking about probability throughout this class, we'll be talking about the relative frequency probability as well as the theoretical probability. We won't really be getting into the subjective probability because that doesn't really lend itself to statistical experiments. And by focusing on relative frequency, we're also looking at the statistics that come from repeatable experiments rather than ones that take people's opinions into account in a large way. Now we've looked at how we can add the probability of multiple events together when the events are mutually exclusive to figure out what the probability that the outcome is in exactly one of those events. So we're going to move forward and figure out how we can come up with the probability of combined events when the events are maybe not mutually exclusive. The additive rule in probability says that if A and B are 2 events, then the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. Now remember, union we read as the word or, and the intersection we read as the word and. So let's take a look at why this rule is the way it is by taking a look at a Venn diagram. So if I have my sample space, S, for my statistical experiment, and then I have an event A, and I have an event B, and I have something in common, that is A intersect B. Now, if I think about my additive rule, what it does is it has me take everything that's in A, so everything there, and then it has me add to that everything that's in B. Now notice the things that are in the intersection have been counted twice. They've been counted by the time that I was counting A, and they've been counted by the time I was counting B. So what we end up with, if we just add them together, is we have everything in A, we have everything in B, we have everything in A intersect B that's coming out of A, and everything that's in A intersect B coming out of B. So we have to eliminate one of these because we've double counted them. And that's why in our additive rule, we subtract out A intersect B, because we've double counted it. Now remember, from our definition of probability, if A and B are mutually exclusive events, then I would have a different looking Venn diagram. I would have A over here, and I would have B over here. And when I went to add them, I'd add everything in B, and then I'd add everything in A, and there's no overlap, so I don't need to worry about this intersection problem. So when I have mutually exclusive events, so A and B mutually exclusive, then I have the probability of A union B equals the probability of A plus the probability of B. And you'll remember from our definition that it's not just that this works for 2 events, it works for however many events we have. Now, if we think back a little bit further, we had a definition of something called a partition. And a partition took our sample space and it broke it into a whole bunch of events, and none of the events had anything in common. So all of the possible outcomes were in different pieces. So this picture is a partition of of S. So this might be A sub 1, A sub 2, A sub 3, A4, A5, A6, A7, and A8. So every single possible outcome of my statistical experiment falls into one of these events. So if I look at the probability that an element falls into A1 or A2, and I keep on taking these unions all the way up to A8, then what I've done is I've put together my entire set S, and with the definition of a partition, all of these are mutually exclusive, and so I get to follow that addition that shows up in my definition. I have the probability of A1 plus the probability of A2 all the way up to the probability of A8 to find out the probability that an outcome from my statistical experiment falls in one of these events. Now, each of these events, they're mutually exclusive from one another, and together they put together the whole set of outcomes for my statistical experiment. So if I add all of these probabilities up, I actually get a probability of 1, which is the probability of my whole set of outcomes. Now, my additive rule was for 2 events. I actually have an additive rule for 3 events as well. So let's take a look at a Venn diagram to help us understand what's going on in this version of our additive rule. So I'll have an event A, I'll have an event B, and I'll have an event C. So now, if I take the probability of my event A, and I'm adding it in, then I am covering the probability of all of the elements here in A. And then adding the probability of B, I am adding in the likelihood of all of the outcomes in B. And then adding to that the probability of C, I'm adding the outcome of all of the events here in C. Well, this would be great, and it is great for some of my outcomes. So everything in A that's not in anything else, anything that's in B and not in anything else, and anything that's in C and not in anything else is now accounted for the exact right number of times. Each one of them is counted for exactly once. However, if I look at the elements in A and B, or the elements in B and C, or the elements in A and C, all of those are accounted for at least twice. So I need to subtract them out because they've been counted twice. So I'm going to subtract out everything that's in A and B. And now the elements in A and B here are accounted for only once there. Then I'm going to subtract out the elements in A and C. So now I've only got a single count of some of those elements. And finally, I'm going to subtract out everything in B and C. So now I've only got a single count of those. So I've subtracted out the double count of the elements here, here, and here. Now, the elements right in the middle here, everything in that center. All right, so the center. A intersect B intersect C. Let's take a look at what happened to those elements. So when I took the probability of A, they got added in. When I took the probability of B, they got added in. When I took the probability of C, they got added in. When I took the probability of A intersect B, they got subtracted. When I took the probability of B intersect C, they got subtracted. When I subtracted the probability of A intersect C, they got subtracted. So these elements, by being in everything, they have now been added in 3 times and subtracted out, which essentially cancels out and they don't exist. So we need to add them back in one last time. So we're going to add them in with A intersect B intersect C, and that will give them the count of 1 that they deserve. So that's where this last part of my new additive rule comes in. All right, one final rule that comes into play is that the probability of A plus the probability of A complement equals 1. So if I take a Venn diagram, look at this, I have my set of all of my possible outcomes of my statistical experiment, and I have some set A. Now remember, A complement is the opposite of A. It's everything outside of A. So if I were to highlight these things, A, the probability of A accounts for the probability of all of the outcomes inside my circle. The probability of A complement accounts for the probability of all of the elements, all the possible outcomes outside of my circle. So once I've accounted for all of those things, then I really have the probability of every single possible outcome accounted for. And I know that that is 1. And so the probability of A plus the probability of A complement is 1. Once you have these rules understood, like what's going on with them, doing these problems turns into a bit of a quick figure out the probability of each event and then plug and chug into the appropriate rule, and you have the probability of the combined event.